All right. So the last time we talked, which was this last Wednesday, we did everything up until chapter or section 5.2, which ended at subplots. So this right here is where we left off. The subplot thing or command, which allows us to make multiple plots inside of the same window. And they're going to use that in the sections to come, so I wanted to touch on that really quickly. So how it ends up looking is the following. You have one plot here, one here, one here, and one here if you set a 2x2 matrix for plots, which is what they did in this command. So it's an m by n matrix, so if you set 2, 2, it will be a 4-section matrix, and each one of these will be a plot. So that is that command, and this is what it looks like if it's a 1x2, or a 2x1, sorry. 2x1 matrix, you get 2 plots in the same window. Alright, and now we move on to the next section. So the next section is all different types of other plots, other two-dimensional plots, right? So the first one that we're going to talk about is a polar plot. So essentially what a polar plot is, it's using polar coordinates, which, they're not used in engineering in Calc 3 you use polar coordinates, but you don't use them as like any sort of plotting. You use them as like a tool to solve questions. And so it's probably not something you're going to see a whole lot of, but just in case, we'll just talk about it here anyway. So what it says is MATLAB provides plotting capability with polar coordinates. So polar plot, theta and r, so it's the exact same thing as before. And that is essentially they just said polar plot instead of plot, and then you set your two variables, which are theta and r for this case. And if anyone didn't know, r and theta are the I think for Calc 3, r, theta, and phi I think are the three variables for three-dimensional integrals, or I think that's what it is. But essentially theta and r is the things in a polar plot for a two-dimensional polar plot. So for our case, theta and r are the variables. And this right here will generate a polar plot of angle theta in radians and a distance r. Alright, and so here's some example for a code. So x is equal to 0 to pi. It looks like 0 to pi over 100, and then it's to pi. Oh, okay, so it's starting at 0. Sorry, it was hard reading this middle part. So essentially what it's doing is it's starting at 0. So r is equal, or theta is equal to 0. And it's increasing the value inside of it. The step part of it is going up by pi over 100. So a very, very small amount of jumps in between. And then it's going all the way until pi. So remember, it's lower limit, upper limit, each integer you're moving up by. And then y is equal to sine x, right? And then if you polar plot this, you get the following down here, right? So that is a polar plot, and this is what it will look like when you when you do a polar plot. You will get this. All right. This is just a practice exercise. It just has you do the exact same things, except that you you just continuously change it, and you end up with a lot of these weird ones right here, like, this. But got a lot of things to go through, so not going to stop too long on those. But essentially, it's just changing the inputs, and you end up with different outputs of these drawings, these plots. So the next one is a logarithmic plot. So logarithmic plots are something that we probably see quite a bit. That's just when you're using log functions, right? So it says, for most plots that we generate, the x and y axis are divided into equally spaced intervals. These plots are called linear or rectangular plots. Occasionally, however, we may want to use a logarithmic scale on one or both of the axes. A logarithmic scale, base 10, is convenient when a variable ranges over many orders of magnitude, because the wide range of values can be graphed without compressing the smaller values. Logarithmic plots are also useful for representing data that vary exponentially. Appendix 2b discusses in more detail when to use the various types of logarithmic scaling. So this is something that you'll see in 401 lab. 401 lab, one of the labs, you have to use a logarithmic scale on one of the y-axes because the values are really small on the x, but the y values are really high, and so you logarithmically scale one of the axes so it still shows up on the plot in a meaningful way. But that's a while off. All right, and so right here, this is the table that tells you the commands here. So it says MATLAB commands for generating linear and logarithmic plots of vectors x and y are listed. So this right here is just the normal plot xy that we've been seeing. Semilog xy, or semilog x parentheses xy says it generates a plot of the values of x and y using a logarithmic scale for x and a linear scale for y. And then semilog y is the opposite of that. So it will generate a plot of x and y using a linear scale for x and a logarithmic scale for y. And then log xy does it for both, right? As you can probably imagine. And then it says, remember that the logarithm of a negative number or of 0 does not exist, although MATLAB represents logs of negative numbers as complex numbers. If your data includes these values, MATLAB will issue a warning and will not plot the points in question. However, it will generate a plot based on the remaining points. So it kind of takes care of that for you. And then it says, usually you will use logarithmic plots with two inputs, both the independent and dependent variables. However, each command for logarithmic plotting can be executed with a single argument, as we saw in plot y for a linear plot. In these cases, the plots are generated with the values of the indices of the vector y used as x values. As an example, plots of y equal 5x squared were created using all four scaling approaches, as shown in this figure right here, which we'll go into in just a second. It says the linear rectangular plot right here. Then you have the I think that's how I did. Let me see. Yeah, this is the log linear and then linear log. So it goes this way. So this is the linear one. Right here is the semi-log x one, which is right here. You can see the bottom is represented in logs, but the top is not, or the y-axis is not. Then down here, you see at the bottom is represented linear, just 10, 20, 30, 40, and then the top is represented in logarithms. And then both of them are represented in logarithms right here. So this is the different type of outputs you get depending on which one you do. All right. So right here, and then this right here, they just tell you how they got this using this code. So it's linear and logarithmic plots display using the subplot function. So they use subplot. This is why I took a second to talk about that at the beginning, because what they did here was they created each of these plots like this, but they subplotted. So as you can see from this command, they did right here x from 0.5 to 50, and then they gave it a function. They subplotted. They did a 2x2 matrix, so they have created this. Now, when you do that, this will all be blank, right? All this will be blank when you hit this command. But what it did was it says it's subplot 221. This right here, this 1 is the position of the very first one. And so then right after that subplot command, they hit plot xy, which what it did was it plotted this function at this location. So that's why this first one ends up here. Now you'll see on the next one, and then they added a title and everything to it, right? And they added the grid. But you'll see on the next one, it goes 222. Because what they did was they did the exact same thing they did for 1, except they subplotted it on the second location, which is this right here. So it went 1, 2, 3, 4, right? And so 222 gets you there, and then they did semilog xy. So this is the one where the x is, the x is logged and the y is not. And then the next one is the opposite of that one at the third position, which is here. And then the last position is the log one. So that's why I made sure to talk about the subplotting thing, to make sure you guys understand that what essentially it's doing is it's just putting these in a position that is predetermined, right? So if you set this to be 10 windows in here, you can tell it to send every one of those figures to this one window. It will show up in one figure window instead of multiple. All right. And so here's an example, but if we have time, I will do one at the end. But right now, like I said, there's a lot of stuff we have to cover, so we'll keep moving for now. But essentially what it's doing is that this question is a rate of diffusion. And so this is something you would see a lot in doing logarithmic questions, is that you have an exponential. And what ends up happening is that you use logs to get it to show up on a graph. And obviously by solving an exponential, it's usually you do a natural log to get rid of it. So things like that, we'll see if that's what this is actually talking about, but I don't know if that's what they're doing. But right here, they do a very, very long solution to this. They say, yeah. So right here, you can see that they did the diffusivity of C and I think I'd say carbon and iron, and then diffusivity of carbon and iron for another type of plot. They did linear. This one was logged. They did the exact same thing, the log y and the log x ones, and then the double log down here of that because of that question. And they got it to show up in one using the exact same process we just talked about in this. Essentially, they did this again, only for for a new question. That was an example. The exact same process. They just had to do a little bit of work to find these answers, right? All right, so this is practice exercises. Not too worried about that. So let's move on to bar graphs and pie charts. So these ones you might use a little bit more often, especially the bar graph. Pie charts I'm not as sure about, but bar graphs definitely. Bar graphs are extremely useful, and they're used a lot. So we're going to talk about that right now. So really quickly, 533 is bar graphs and pie charts. So it says bar graphs, histograms, and pie charts are popular forms of reporting data. Some of the commonly used MATLAB functions for creating bar graphs and pie charts are listed here. So once again, guys, if you need somewhere to go to find these, like let's say you forget how to make a pie chart or a bar graph, this is it. Also, I don't know if it's in the notes I posted, but it is also in the help window, which I will go and show at the end of this, where you can find these. Because some people said the help window is not very effective, but I would think that you have to know what you're looking for, and that's where a little bit of background knowledge comes in. Because if you go, I need to make a chart here, but don't know what type of chart it is, it might be more difficult to find something in the window, the help window. But if you know exactly what you're trying to do, it's probably a little easier. So table 5.5, it says bar graphs and pie charts. So right here, bar x, where x is a vector, bar generates a vertical bar graph where x is a two-dimensional matrix. Bar groups the data by row. And then you have bar h. When x is a vector, bar h generates a horizontal bar graph. So this one will be going from side to side, right? This one vertical. The difference is that there was an h. H probably stands for horizontal. And then you have bar 3. This one will generate a three-dimensional bar chart, right? So that's good. It'll probably look something like this. And then it says bar 3h. This is a horizontal three-dimensional bar chart. And then you have pi x generates a pie chart. Each element in the matrix is represented as a slice of the pie. And then you have pi 3, a three-dimensional pie chart. And then a histogram generates a histogram is the last one. So right here, these are our graphs of vector x, a bar graph of matrix y. So this is the first one I think they did. So this is a vector x, and then they did a bar graph of a matrix as well, which I think, where did they do that? Yeah, so right here. So essentially, they showed you two versions of the same command. So they just did bar x here. The first one is x is a vector. So this is the vector x. Then when x was a matrix, you get this. So this is essentially two sets of data, right? It's one set and another set, depending on the row. And then this right here was your three-dimensional bar chart. And then this is your also a pie chart for x. And you can do the exact same thing with subplots. You can get them to all show up in one figure, as they showed here, using the subplot command, just like normal. And then we have histograms. So histograms is a plot. So I've I very rarely, so histograms I've very rarely seen. I usually see more bar charts than histograms, and some of you will probably be wondering, they're like, what the hell's the difference, right? It looks like they're both bar charts. So really quickly, since I don't really know much of the difference, we're going to read it. So it says a histogram is a plot showing the distribution of a set of values, especially useful in statistical analysis. In MATLAB, the histogram computes the number of values falling into a number of bins. Categories that are equally spaced between the minimum and maximum values. For example, if you define a matrix X as the set of grades from the introduction of the engineering final, the scores could be represented in a histogram shown in this. Now I know what the importance is. So essentially, what it is saying is that it essentially takes a set of data and it shows where the scores end up, right? Or not scores, but like any set of data. So for example, if you look here, in between 0 to 30, there was one person, right? Because we're at this one mark here. So these are the normal. This is a normal set of grades. Between 0 to 30, there was one person. Between 30, I guess you'd say 31. So 31 to 60, there were two, and so on, right? And so essentially that's how you read them. So they're a little bit different than bar charts in that respect. And once again, you can see here is that you have grades. All these grades are specified in a location using the same thing we have been using, which is the subplot command to get them to all show up here. All right. And then it says histograms represent the distribution of data. So the first one right here is grade data using the histogram function with default parameters. B, the number of bins specified, right? And then C, the bin edges specified, and then the bin edges specified but normalized, that's a lot of I's in here, so that the area of each block corresponds to the number of items in each bin. Wow, that's a lot. So essentially, you can specify, so this is default. The default one will just have them right next to each other, essentially. Then right here, if you specify the bins, what they mean by bins is, so really quickly, let's say you had 5 bins in front of you, and you had 20 grades, right? And they ranged from 0 to 100. Your first bin would be 0 to 20%. Second bin, 20 to 40, or 21 to 40. Next one, 41 to 60, 61 to 80, and so on, right? So 81 to 100. And essentially what they mean by bins is that you're taking each one of these grades and you're dropping it in to the bin, like not a garbage can. I don't want to make you guys sad, but essentially you're dropping them into a can in front of you, and that's how they're creating this plot. That's what a histogram means, is that essentially they're creating them into little categories. Let's use categories. That's a much better word. Not garbage bins, but categories. So that is what they're doing here. And if you specify the bins, it looks like this. So it looks like, just looking at this, is that there was nobody between 30 something to 55 or something. There was nobody in between here. And so you can look at this like that. All right, let me see. And then it says, so right here is the histogram function. Sorry, because I was discussing that. But so right here it says this is how you would do it. So if you said X is equal to, these are all the exam scores, by the way. All the exam scores are the following right here: 100, 95, 74, 87, 22, 78, 34, 82, 93, 88, 86, 69, 55, 72. That is an X, which is an array of values, essentially, of all of those, right? And if you do histogram of X, it will throw all of them in here. And it will do by categories. Now here, this one right here is the histogram function determines an appropriate number of bins automatically is the first one. The second one, though, you can create a histogram with the 5 bins, and that would be histogram X5. And that is the 5 categories. And so, since you know that your maximum is 100, right, it will essentially, so let me see, this says the results are shown in that 52B, which is here. That is the results of putting these numbers into a histogram with 5 bins, like we said. And then it says, although it usually makes sense to space the bins equally between the minimum and maximum data value, sometimes it's more meaningful to define the bins based on some other criteria. For example, consider the grade data. It would be preferable to define each bin so they correspond to specific grades as follows. You see? So, right here, if let's say our grades, so this right here are the bins, essentially. We have now made bins for the grading value. So 0 to 60, F, 60 to 70, D, so on, right? All the way up. So these are all the grades. Then it says you can define the edges of them. So, for example, histogram, you have 5 bins still, but you define the edges. The edges would be 0, 60, 70, 80, 90, 100. And since you've done that, then you do histogram X, that same array of values for us before, but only you do edges. Essentially, you created a new variable here, edges, which are all the data sets. Instead of just putting 5 here, where it creates 5 equally spaced ones, it created the ones that you told it to, which is 0, 60, 70, 80, 90, 100. And by doing that, what will happen is you will end up with a histogram that shows you the number of people that got A's, B's, C, D's, and F's, right? Which, if you look up here, it looks like from 0 to 60, you had 3 people. From 60 to, I guess, 70, you had 1, and then so on, right? You just read it like this. And then it says, notice that the 3 scores fell between 0 and 60. That 3 of the scores fell between 0 and 60. Yet, at first glance, the left bin looks much bigger than the rest of the other results. An alternate way to represent the data is to make the area of the bin proportional to the number of values in the bin, using a normalization scheme. So you can do histogram, X, edges, normalization, count density. So what that's going to do is it's essentially going to represent this graph in a proportional way. So, for example, there were a lot of scores, right? If you go back up here into our regular data, there are what? How many scores is this? It's 3, 6, 9, 12, like 14, right? If you looked at this chart, you would think, damn, man, everybody failed, right? You would think everybody failed because we went from 0 to 60, and this is a huge part of the pie, right? But it's not true. Only 3 people were between that. So by doing the normalization of it, using that command we just showed, you end up with this. You end up with a way smaller piece, right? And it sort of normalizes it to make sure it doesn't look misleading. Because this right here looks misleading. You would think everybody failed, right? And it would look like that, but it doesn't. That's not exactly what it means. So let me go over that really quickly again. So it says histogram. You specify your variable X, the edges of the histogram, and then you do in single quotes, normalization, comma, or once you finish it, make sure you always finish your single quotes, then you comma, single quotes, count density. And so, once you do that, you get setting the results of the histogram function equal to the variable creates a handle to the plot. You can think of the handle as a nickname. Handles are covered in more detail in the latter chapter. If you would like to save the plotting data, save as the number of values in each bin, use the hist counts function. So if you did A is equal to hist counts, so that would be the histogram counts, it will count the number of people in each bin, right? And where's this one at? Yes. So using the first figure, this right here, this is the data represented in the first picture. So there is 1 person between 0 and 20, and then 2 between the next one, 8 between the next one, and then 3 at the last one, right? So this is what it's going to do. It's going to tell you the number of counts inside each one of the bins. Weight of, oh man. So this is an example using weight distributions of the average 18-year-old American male. There's no way. 52 pounds? I don't know about that one, guys. I do not know about that. So the average 18-year-old male weighs 152 pounds. So what they did is they take this data, and it's in a weight file, and it shows the range of data here. And what you end up getting is a histogram representing each of the different bins for each weight value. And so right here, they subplot it and they do this. So really quickly, I'll kind of put this into English. So then they loaded the weight data right here. And then they create a subplot of essentially a one row with 2 columns, right? And they put the first one in 1. They plotted weight. They just plotted weight variable, which is what they get from using the weight data. And then they put a title, a label, and a X label and a Y label, and they did a grid on. Then they created the histogram. They put the subplot, once again, they subplotted it in 1, 2, 2, which put it into the bottom right-hand corner, or the right side of the window. And they did histogram of the variable weight. They X label and they Y label and they titled it again. And this is what you end up getting. So this is the weight of freshman class men. Anyway, you can see where all of them sort of fill out. So it looks like this looks like a distribution, right? Essentially, like if you looked at this as a set of data, which is really what this is, right? It's a distribution of across a bunch of different people. Is that this looks like a normal distribution, essentially, right? They said the average was 150 pounds. It looks like that's right where it is, right? So this right here is a distribution of a set of data, which is, I think, what they said was the point of a histogram at the beginning anyway. All right, so now we are on to the next one. So it says 535. XY graphs with 2 y-axes. Sometimes it is useful to overlay 2 XY plots onto the same figure. However, if the orders of magnitude of the y values are quite different, it may be difficult to see how the data behaves. Consider, for example, a graph of sine of x and e to the x drawn on the same figure. The results obtained with the following code are shown in here. So let me see. Yeah. So they did x. They set up, once again, that range. From 0, they stepped up pi over 20 every time, and their final one was 2 pi, right? So that was their range. y1 was sine of x, y2 was the exponential of x, and then they subplotted it once again. They plotted x, y1, and x, y2, okay? So this is where you end up, right? So right here is the problem, is that by doing that code, you end up here. So this is an issue, right? The issue is that you don't actually see something very useful, right? In my opinion, in this first one, it doesn't really tell you much. So what the point is that by having 2 y-axes, you can scale them differently. And so it says MATLAB allows the y-axis to be scaled differently on the left-hand and right-hand sides of the figure. A, both lines were drawn using the same scaling. So like I said, this does not seem very useful. Because if you guys are aware, is that essentially sine, as you guys know, travels back between two numbers, essentially, right? Or numbers. It doesn't, essentially, the exponential changes. So the scaling had to be changed to the exponential here, because the exponential goes really high. And the problem is that this one does not. The sine of x function does not. And so the problem is that by doing that, you end up with a near straight line. Essentially, this looks like a straight line to anyone, but it is not, right? Because we know it's a sine function. A sine function looks like this. So essentially, we have to scale in and move closer to be able to see the full picture. And so that's what having 2 y-axes can do. You end up where this one is scaled, right? So this one over here is scaled to the exponential function, right? You guys can see the whole exponential, right? It gets asymptotically to 6, it looks like. So essentially, it goes and approaches 6. Let's just say that. I don't know if that's true, but essentially it looks like it approaches 6. This one right here doesn't look like it does anything, right? It's a straight line. It looks like, y is equal to 0. Or x equal to 0, whichever one. No, it's y equal to 0. So essentially it looks like that. But it's not. It actually looks like this. And so having 2 different y-axes can help you compare two different, very different equations, like a sine and an exponential, right? So right here, let's go through the code. Once again, they set that up. I've already explained that. And then it says the plot of sine x looks like it runs straight a line, x equals 0. Oh, I was right. It was x equals 0. Because of the scale. The y-axis, so y-axis function allows us to create a graph with two y-axes. So if anyone ever needs to know, essentially just pick up the, if you'd ever need to know what any function is for creating a table, just think of the most unoriginal one and you'll probably be right. So two y-axes is just y-axis. So this function allows us to create two y-axes, one on the left and one on the right, by specifying which axis to use. Okay? So once again, they subplotted 1, 2, 2, so a 1 row, 2 column subplot. And right here, they said plot x, y1. X label, right? X label x, y label sine function, y-axis right. Okay? So essentially they said to do the double y-axis, they specified the right side, right? And so plot x, y2, which y2 looks like over here. So they have y2 and y1, so sort of remember these as we go through. And then it says y label exponential function. So if we go up here, this is the bad one, right? This one tells us nothing. This is the good one because we now have one function right here. So essentially we can still see that the exponential goes up to this same value, right? On both sides, you can see it now. But you can also see that the sine function goes to here using this one. So essentially when you create this, you have to know which function you want to show up on either side, right? But that's not really a big deal. You could have just have easily had the exponential function over here and it would have been fine. But essentially when you read this though, so this is the important part, when you read this type of chart, you have to know which one is representative of what, which scale is representative of what. Now for this one it's quite easy, right? Because sine functions obviously go back between 1 and 0, right? So pretty straightforward that, or 1 and negative 1, sorry. 1 and negative 1. So you can kind of follow this. But here at the, if it was another type of, I don't know, another thing you were trying to show, like let's say two exponential functions, but one ended much earlier than another one, you would have to then know in your mind which one needs the higher scaling, right? But I think everyone can kind of see why this one's more useful than this right here, because this one tells you pretty much nothing. All right. So really quickly, this is another example. All right. So now let's do function plots. So this is the last part of two-dimensional plots. So we are 32 minutes in, so going okay. So two-dimensional plots, last one, function plot. So it says the fplot function allows you to plot a function without defining arrays of corresponding x and y values. For example, if you do fplot, man, it looks like it has an @ sign there. It's hard telling though because of the font they use. But essentially it uses fplot x sine of x, and then it's comma 2 pi, 2 pi. So let me see this. Yeah, so essentially it creates a plot of x. It's x versus sine of x for x values from negative 2 pi to 2. Okay, so I think I see what they're trying to say here. Essentially, I think what this is, yeah. Okay, so essentially what this is, this like @ sign is essentially what it's saying is that it's x sine of x, so it's its own it's its own variable. So essentially you're saying x versus sine of x. That's what this first part is saying, and then you had to specify the range here. Yeah, that's what the first one is here, but they change it up down here just a little bit, but we'll talk about it in a second. It says the first argument in the fplot function starts with the @ symbol to specify the independent variable, so it is an @ symbol, and continues with the function to be plotted. So the independent variable in this case is x, right? The second argument is an array defining the plotting range. Oh, wait a minute. Function start that to specify the independent variable. The dependent variable is sine of x though, so yeah. And then it says the second argument is an array defining the plotting range. For more complicated functions that may be inconvenient to enter in this way, you may define an anonymous function and enter the function handle. Anonymous functions and function handles are described in a later chapter. Got something to look forward to. devoted to functions. The correct syntax for this case would be, so you have here, f is equal to @x, sine of x. And then if you did f plot and just put in f here, this part is already put in. So you don't actually have to do that first part if you made a variable f, or if you did @x, sine of x. But I don't see, either way is fine. And so this is what you end up get with an f plot. All right, and more practice exercises. So we are done with this. So we have about 15 minutes, to do the next really quick chapters. So let me get to those. So we have three-dimensional plotting. This one is another quite long chapter, but let's do a three-dimensional line plot. So it says, let's start here. So it says the plot3 function is similar to the plot function, except that it accepts data in 3 dimensions. Instead of just providing x and y vectors, the user must provide a z vector. These ordered triples are then plotted in 3 space and connected with straight lines. For example, right here. So you have x is lin space 0, 10 times pi to 10 to 1000. So this is 0, 10 pi, 1000. And then you have y is cosine x, z is sine of x, and then you plot all 3 of these variables with plot3. Remember, this is plot3. And you turn on the grid, and then you can add labels. So you have x label, y label, z label, title. And right here, as you can see, they created a spring, and so that's why it's named a spring, right? And this is a 3D plot of a spring, as they said. So essentially, the difference between this one and the previous one is that you now have to specify 3 arguments, and it's plot3, okay? And now right here, these are some 3-dimensional plotting commands. So plot3 is the one we've already talked about, and then it says comet3 is x, y, and z, generates an animated version of plot3, that's fun. And then you have mesh z or mesh x, y, z creates a meshed surface plot. Surf z or surf x, y, z creates a surface plot similar to the mesh function. Shading interpolates between the colors to illustrate surface plots. Shading flat colors each grid section with a solid color. Color map name allows users to select the color pattern used on surface plots. Contour z or contour xyz generates a contour plot. Contour f z or contour xyz. I wonder if there's supposed to be an f here. That might be a typo, because it would be the same function as here. Yeah, this should be an f. So it should be contour f z or contour f xyz creates a filled contour plot. Surf c creates a combined surface plotter and contour plot, and then p color z creates a pseudo color plot. A lot of plots here. So I guess we got to go through these. So right here we have a surface plot. So surface plots allow us to represent data as a surface. We will be experimenting with 2 types of surface plots. We have the mesh and the surface plots. So mesh plots. So it says here there are several ways to use a mesh plot. They can be used to good effect with a single 2-dimensional n by n matrix. In this application, the value in the matrix represents the z value in the plot. The x and y values are based on the matrix dimensions. Take, for example, the following very simple matrix. So right here. This is our matrix. They have specified z as being all of this, right? And then it says the code. You would do mesh z, x label, y label, z label, whatever you wanted, right? And this is what you would get. You would get this as a surface plot. Essentially, you can see it's kind of like, sliding across back towards the back right over there. And it's this surface, right? So that is the surface plot, or mesh plot, sorry. But they're all surface plots, I guess. But mesh plots look like this. And then it says the graph is a mesh created by connecting the points in a defined z in a rectilinear grid. So this reminds me of something that we did in FEA class, which is a later class for finite element analysis. When you can create it's kind of skeleton drawings where you just define points in 3D space, and then you can connect the points using lines, and then you can have it fill in the lines with like some surface, right? Just a surface that you can specify as a material. And it kind of looks like this. Essentially, if you had a point here, point here, point here, and point here, what it's doing is it's just connecting lines that are specified by the points in the matrix, just connecting them and creating this surface. Now, really quickly, I have a hard time thinking that any of us will use this unless you get into like some like heavy research. Maybe I'm trying to think. I've never used a plot like this, so I don't know where you will. But I think I've seen a plot like this for like for my senior design for RFID. For someone did an RFID like little thing for our senior design project, and something looked like this. And I don't quite remember what the context was, but I think he made something like this. All right, so then it says, notice that the X, so I'm restarting where I was before, the rectilinear grid. Notice that the X-axis goes from 0 to 10, Y from 1 to 3. The matrix index numbers were used for the axis values. For example, note that Z15, the value of Z in row 1, column 5 is equal to 5. The element is circled on figure 528. The mesh function can also be used with 3 arguments, mesh x, y, z. In this case, x is the list of x coordinates, y is the list of y coordinates, and z is the list of z coordinates. So they did x, linspace, 1, 50, 10, y space, 50, 1000, or 500, 1003, and then z is all of these right here. I think it's that same one as before. As a matter of fact, it looks like it is. And then it says, the x vector must have the same number of elements as the number of columns in the z vector, and the y vector must have the same number of columns in the rows in the xz or in the z vector. And then you do the command mesh xyz, and you would get this right here. And it says, notice that the axis varies from 0 to 50 with data plotted from 1 to 50. Compare this scaling with that in the previous 528, which used the z matrix index for numbers for the x and y axes. So it looks the same, but the scaling's different, is what they're trying to say, essentially. All right. So then we have surf plots. So surface plots is what they're saying. Surf plots are similar to mesh plots, but surf creates a 3-dimensional colored surface instead of a mesh. The color varies with the value of z. The surf command takes the same input as mesh, either a single input, for example, surf z, in which case it uses the row and column indices as x, y coordinates, or 3 matrices, like we just did. It says figure 5.29b, which I believe is this right here. Where's b at? B. Was generated with the same commands as those used in generator to 5.29a, except that surf was replaced to mesh. So right here, this was like our first one. This right here is the colored one, as you can kind of see that, I guess, okay, maybe you can't see it, it's in black and white, but use your imagination, they're shaded differently, right? So this is probably colored, okay? Okay. So then it says the shading scheme for the surface plots is colored or controlled with the shading command. The default shown in figure 5.29b is faceted. Interpolated shading can create interesting effects. The plot shown in figure 529c was created by adding this shading interp, which was a command we saw earlier. And so you end up with a more. So this is interpolated value. So essentially it's less sharp edges, right? As you can see, there's like sharp lines here. It's none of that. It's kind of like a smooth surface across. And then it says flat shading without the grid is generated with shading flat is used, which is in the last one right here. And then it says the color scheme used in surface plots can be controlled with the color map function. For example, you can do color map gray forces a grayscale representation for surface plot. This may be appropriate if you're making black and white copies of your plots. Other available color maps are all of these. And then you can help color map, and it will tell you about what all of these sort of look like. But I would say, so summer? So you could say color map summer, color map winter. I don't know. But this is all the stuff you got. This is what we got. Color map flag. Could you red, white, and blue? It's very patriotic. All right, and then it says another example. So a more complicated service can be created by calculating the values of z. So we have x. This right here is our defined numbers for x, same as y. X and y is mesh grid, x and y. If you remember the mesh grid command that we did previously from the matrix chapter, you have x and y is equal to mesh grid x and y. And then you have z is equal to x, matrix multiplication, remember, dot x or dot multiply, of x, negative x, to the second power minus y to the second power. And then it says in the preceding code, the mesh grid function is used to create the two-dimensional matrices x and y from the one-dimensional vectors x and y. The values in z are then calculated. The following code plots the calculated values. So right here. So let me see, they once again did a subplot of all of these. So they did subplot 221, which is the top one, subplot 222, which is this one, and they just changed a little bit. They did a mesh plot for the first one, and then a surface plot for the second one. And then it says either the xy vectors or the xy matrices can be used to define the xy axis. Figure 30a of 530a is a mesh plot of the given function, and 530b is a surf plot of the same. So this is what you end up getting. Which is funny because where you see something like this, at least where I see it, I usually see this in like representations of like space. This looks like sort of like a black hole kind of thing because they generally like to represent, like in like astrophysics, they like to represent space as like a single layer and how it gets warped around an object with like massive gravity. So this is what they usually like to represent it as, which is pretty neat. This must be how they create it in some way. All right, and then we have surface and contour plots are different ways of visualizing the same data. So it says contour plots. So let's move on. Like I said, we're almost to the end of this chapter. And then it says contour plots are two-dimensional representations of three-dimensional surfaces. So for example, it's just the top, right? So essentially they project down these values. It's sort of like in your introduction to Autodesk class or like AutoCAD 102, I think is what it was. Some of you might remember. We had times like this where we used projections to see what shapes looked like, and you projected from 2D or 3D down into 2D, or 3D into 2D, sorry. And so that's what this is. Essentially, you're taking this 3D plot and you're projecting its values down, and it ends up looking like a circle. So essentially, if you look at it from the bottom or look at it from the top, I don't know how they project it. It looks like from the top down, you end up getting these right here. And so really quickly, let's go through the code. It says the contour command was used to create figure 5C, which we just looked at, 530C, and the surf C command was used to create the last one. So once again, they subplotted, they put 223, which is in the third position. They did a contour of X, Y, and Z. They labeled it, and then they subplotted 224, the last one, which was the combination contour, which was the very last thing we went over in that big chart at the beginning. This is the combination of the surface and contour plot. So you can see the contour plot at the bottom here, and the surface plot is still on there. And so this one is pseudo color plots, which I have no clue what that is, but we'll see here in a second. It says pseudo color plots are similar to contour plots, except that instead of lines outlining a specific contour, a two-dimensional shaded map is generated over a grid. Oh, okay. So MATLAB includes a sample function called peaks that generates the x, y, and z matrices of an interesting surface that looks like a mountain range. So x, y, z equals peaks. With the following code, we can use this surface to demonstrate the use of pseudo color plots. Wow, this is not... I don't know how much I like this one, if I'm honest. Yeah. Alright, real quickly, you're never going to have to do this. So, we're probably just going to move on. I will never give you a question like this. I have no clue where this could even be. Essentially, okay, really quick, what the difference is that instead of these outlined shapes at the bottom of a contour plot, or like this right here, they fill it with three-dimensional shapes. Or not three-dimensional, two-dimensional shapes. So essentially you end up getting like actual like little hotspot zones here. That's the difference. But I don't think that I would ever have you ask to do that, because that seems really strange. But use the same, you use the functions that were defined in the table, and you do the exact same things, like, you know, color, shading, all those commands apply for this as well. But we're going to move on because we're running out of time. Okay, so this right here is really fast, so let's do that. So editing plots from the menu bar. It says, in addition to controlling the plot, the way your plots look by using MATLAB commands, you can edit the plot once you created it. The plot in figure 532 was created using the sphere command, which is one of several sample functions like the peaks one used previously. So this is what you get using the sphere command. And then they plotted it in a 3D plot, right? This is what you end up getting, and you can change. So once you get it, you don't have to use the code. So that's what this whole thing is for. You don't have to use the code to add the labels, legends, and all that stuff. If you don't like to remember that, you can just do it from here. So for example, there's the toolbar at the top, X label, Y label, Z label, Titan, legend, color bar, all this stuff. You can do it from here as well. And honestly, when I used to do these in the class, I used to do them from here. I just would create it and see if it looked right. And once I figured it looked good, I would add the labels. And yes, you can do it all through the code. That's fine, but I was worried about just getting something to show up, right? Like my worry wasn't titles, right? It was getting even a plot to show up. So if I got this, I was very happy, and so I would just add my labels afterward. So, but the important thing is that you add them, because let's say you had this data set right here. Let's just say this is like a representative of something, and you have no labels. Your chart is meaningless. It means nothing. Like, there's nothing to describe what any of these scales mean. Nothing. So this is a useless chart. Even if let's put it this way, even if this chart told you the secret to life and how you could all find happiness, if there were no labels on here, do you think you guys could use it to find happiness? Probably not. So this is why it's important to add your labels, because if you don't, we'll never find happiness. So moving on. Let's do this. So right here, use the sphere command, which is what they did. And it says, in the figure window, so let me see what they moved on to here. It's kind of hard to say. In the figure, the insert menu has been added. Notice that you can insert labels, titles, legends, text boxes, and so on. The tools menu allows you to change the way the plot looks by zooming in or out, changing the aspect ratio, and so on. So this is a zoom out. Essentially, they've zoomed out here. And it says the figure toolbar underneath the menu toolbar offers icons that allow you to do the same thing. The plot in 532, which I believe is this one right here, doesn't really look like a sphere. Agreed. It's kind of a smushed one. And it says it's also missing labels and title because we don't know what the meaning of life is. And the meaning of the colors may not be clear. We edited this plot by first adjusting the shape. So you can adjust the shape, zoom it out a little bit, and now this looks more like a sphere, right? And so what they did was they went to Axis Properties, Property Editors, Axis Window, More Properties, and they did Aspect Ratio. And they changed basically everything, right? Just to get it to look right. Because right there, it did not look like a sphere. This looks like a sphere, right? And they added a color scale here. So essentially what this does is that if you read this color scale, you can see where you're at on this chart. So for example, kind of hard to see because this thing's in the way. But as you can see, -1, which you would imagine is like, down here, right? You can see that the color scale represents where you are inside of here. So for example, 0 looks like to be white. If you draw a line like right across the middle where zeros are, you end up in the white, right? That's what it's saying. It's a color wheel that helps you figure that out, a color scale. And this is something that you'll see a lot of in FEA. Whenever you start doing like simulations of designs, there's usually a color scale that's attached to it that tells you if you're where the like sharpest like stresses are, like where the most stress is being located. and it helps you locate it faster using the color wheel. So for example, most programs are like green. If it's green, it's fine. If it's red, that's where it starts to become like a problem. And they use the same thing in factor of safeties. So for example, if you are, let's say your factor of safety is less than 1, right? Like for example, what that means is that let's say your design is meant to hold 2,000 pounds and you put 2,000 pounds on it. And if let's say it's all green, the whole design's all green, which means that it's fine. It's over the limit, right? It's over the factor of safety of 1.5 or whatever, which means that it could hold 3,000 pounds or 2,000 pounds. I think I said 1,000 to begin. But essentially it could hold 1.5 times the amount that you put on it. And if you then if there's anywhere that's red, it means that it's below that, which means that it will fail when putting on that 1,000 pounds or whatever I said at the beginning. And so that means you have to add more material or change a shape to that spot. And so this color thing, it's very important that you figure out how to like read these, because they are extremely useful and you'll show up in a bunch of classes. I recommend taking FEA, by the way. Really good class, very useful. And Dr. Chu is a great professor, if you have him, if you're lucky enough. All right, so really quickly, this is creating plots from the workspace window. We've already done saving your plots, so we're done after this one. So it says creating plots from the workspace window. A great feature of MATLAB, they really talk themselves up, don't they? Is its ability to create plots interactively using the variables in the workspace window. Select the variables you would like to plot, then select Plots tab from your MATLAB desktop, shown in figure 5.3. So right here, and they went up to plots, so home, plots, apps. And it will list plotting options it thinks are reasonable for the data stored. Simply select the appropriate option, use it, and your plot is created in the current figure window. If you don't like any of the suggested types of plot, choose the drop-down menu and a new window will open with a complete list. So essentially it's sort of like Excel, where you can create plots. There's there's like a figures tab in Excel where you can find like scatter plots and all that type of stuff. And it has the same thing here, as you can see at the top. So plot, pie, scatter, all this stuff. There's the semilog X, semilog Y, double log. So it's got every one of the plots that we've done so far. And then it says this is especially useful because it may suggest options that had not occurred to you. For example, 535 shows a scatter plot of the X and Y matrices highlighted in the figure. The matrices were created by loading the CMount dataset, which is built into MATLAB. So that's like a program. It's a included program, or an included code. It's sort of like the peaks function that we've used before and the sphere function. And this is what you get out of it. And so they plotted this from the workspace, as you can see here. So there are other ways to do these plots. If you, let's say you find the answer, right? Let's say you find the answer, you get down to it, and it ends up over here, because that's where it ends up, right? When you find a solution, they all end up over here. If you don't remember the plotting command for some reason or another, and you just can't remember how you're supposed to do it, and the help window doesn't show up, and have no fear, you can just click on it and go up here and create your plot, the one that you're supposed to create. There's other ways to do it, and I will not punish you for doing it one way or the other. Now, I would like for you to try to do the code, right, as best as possible, but, as long as you can generate it, I'm not too worried about it, because the goal is that you can generate it, right? If you can generate it, that's a problem, but if you can, good for you. We did it. All right. And so we've already done saving your plots, which was the one that we did at the very last part of the class. So this just tells you how you can save all of these as either a figure file, a JPEG, enhanced metafile, all types of stuff. You can copy it, paste it into a Word document, whatever you want to do. But this one right here, I would avoid. Avoid this first one. And the reason is because if you ever have to reopen it, you have to use MATLAB. You cannot use anything else. MATLAB is the fig file is a specific MATLAB one, and it killed me when I took the class. As I explained in the last class, that I had to come back and open MATLAB. I had to drive to school at like 9 at night just to do that. So don't be like me. Use a JPEG or some other file that's accessible to you. All right. So that ends the rest of this lecture. This chapter is over. Sorry it took so long, but there was a lot of things in here. Plotting is something that's a very major part, of MATLAB, and you'll use it in many classes, or at least a couple, at least 2 or 3, I would say. And it's a good way to generate data and make it easier to digest. So thanks for listening if you did. We will be back next week with our next chapter, which is user-defined functions. All right? Thanks, guys.